Two questions here. One of them actually, this second part, if you remember, we used it to abstractly justify this interesting phenomenon we observe in two-dimensional spaces, that in two-dimensional spaces there is no skew lines. I mean, you could construct two lines which are skew in 3 dimensions, but you can't produce those two on the plane. It seems like a trivial fact for you because you know two-dimensional spaces very well. But we abstractly justify this with the help of this second part of this lemma. If you don't remember that, no, it's not on YouTube yet, but it will be there soon. So we'll just look at this, how we can see this proof, how we can see this lemma. 2 parts of it. I'll prove them separately. First, we'll focus on the part 1. Secondly, we do part 2. Right, so let's just look at the part 1 first. It says this. Imagine we have a set of vectors which is linearly dependent. I just recall the definition for you up there, and I'll recall it again here in the course of the proof. We have to show that in this set, if it is linearly dependent, I can always find a smaller, if you don't know this symbol reads subset. This one reads subset, this kind of symbol, and I put this extra not equal, which means that it's proper subset, so it's not equal to the set itself. So it's a proper subset, so you can throw out some vectors from your set, and with no expense at all. So you throw out the vectors, but the span of the smaller set will be equal to the span of the bigger set. Generally, if you have vectors, if you have like 5 vectors, if you span them, if you throw some of them, the span generally seems to be smaller because you have less vectors, less coefficients to play with. But the interesting fact about the linear dependent sets, if you can wisely drop the vectors from it, and still keeping the same richness of the span will be as rich as your original span. Let's just look at that. It's a simple proof. It's not a big deal, but it shows you normally how you frame your solutions or argument involving spans and linear dependence, and there will be a few in your yellow book. That's why I chose this one, just to show you the way we present this, in order for your tutor to be able to understand what you're saying. So what I will do is this, because this set is like I'll give the names to the vectors which are within this set. So let's just say my set has m vectors like this. We know the set is linearly dependent. So it means what it means. By definition, it means that I can produce coefficients, lambda 1, lambda m for each vector, one coefficient, real numbers with two properties. One of them is that not all of them 0, right? And the other property is, if I take the linear combination of my vectors with these coefficients, the result will be 0 vector. Again, they are linearly dependent. That's the assumption of this part 1 of lemma. So we have coefficients, not all of them 0. For simplicity, because my exposition right now is symmetric, I can assume that lambda 1 is non-zero. If it's not lambda 1, if it is, for instance, lambda 2, I can just re-index my vectors and re-index my coefficients with the different indexing sequence. So I can always think it's just the first one which is non-zero. And that's a very nice way to present your proofs, actually, this kind of, when you say these things, because it makes it much more clear. Right. If I know that this lambda 1 is non-zero, the step which I can do now is I can solve for this. We did it a few times, and that's the very typical step which involves linear dependence. If you know that one of them is non-zero, specifically lambda 1 is non-zero, you can always solve for the vector standing next to this coefficient. If I solve, because if it's non-zero, I can divide by it, by this coefficient, the result will be all of these vectors will go on the other side, here, on the right-hand side, and then I'll divide by lambda 1, and the result will look like this. That would be the coefficient next to the A2 vector. This lambda 2 with negative, because it went to the other side, and by lambda 1. And for instance, the coefficient here will be like this. So it's a negative because this term went on the other side and divided by lambda 1. Good. Now let's just see why this is true. Why these two equal to each other. I mentioned this already. We obviously have this simpler observation because this S no, never mind that. Let's just do it differently. What I will do is this. I'll take a vector now from the span of S, like this. Definition of span says to me that this vector has this form. I can find numbers 1 to m, and this time I use the x letter for that, such that this vector x, which is taken from the span, is actually equal to the linear combination of these A vectors. That's basically the definition of span. Vectors in the span, it's all possible linear combinations of your given m, a, a1, a2, am vectors. So if you take one of them from the span, it will be some linear combination which produces this vector. Now, what I will do now, I can substitute this a1 with the expression for the a1 we come up with from the linear dependence assumption. If I sub in here the expression for the a1, it will be a rather lengthy expression, but look what it will be. Look at this. It will be x vector equal x1, this x1, then goes the expression for a1 vector, this long expression, this one, then goes the rest of it. So then goes this piece, dots, this piece. Here it is. A2 component, dots for the rest of the components, and the last component. But now, what I can do, I can just rearrange this thing, and I can combine all of the A2s together. We have two instances of A2. All of the A3s together, A3 will be next here, and the A3 will be next here. All of the other vectors together, including this last one, AM, and is this AM. If I combine all of them together, but look what will happen. For the A2, the combined coefficient will be x1 negative lambda 2 on lambda 1, and this x2. So the combined coefficient is this for the A2. For the A3, it will be similar combined coefficient. For all of the vectors under these dots, hidden by these dots, will be some sort of coefficient like this. For the last one, it will be x1 times this fraction and this xm. So the combined coefficient next to the am will be like this. Good. There's a lot of writing on the screen, but at this stage, what I think we can let's just put it this way for you. Look at this identity. How we can interpret this identity in a span language. What does it say? It says to us that x vector, this x vector, equal to linear combination. Look at this. It's a linear combination of the vectors a2 through to am, no longer a1 involved, with some coefficients. They are lengthy brackety coefficients, but still some coefficients. So what we see here is, in fact, x turns out to be a member of the span of the smaller set like this. Look what I started with. I started with the x in the span of S, so in the span of these m vectors from a1 to am, and through these two lines, I came to the conclusion that x is in fact a member of the smaller set, or span of a smaller set with no a1 involved. And the crucial step in this two lines reasoning was this expression for the a1 in terms of a2 and am. In fact, actually, this line can be said simply that actually a1 vector, this a1 vector, is also a member of this span. And that finishes the proof. You see what happened? We had my set S with m vectors. We dropped a1 vector from this set. We dropped this a1. We ended up with a smaller set, but the vector still belongs to the span. That's why the span of this S1, and this S1 set now is the set which has all vectors but a1 vector. This span of S1 equal to the span of S. And that's where the proof finishes. You have to spend some time with this. It's not an easy proof for the experienced person with the linear algebra. I'd say it's a very standard way of doing things with the span and linear dependence. We did some smaller version of this kind of argument already with you when we discussed with you what happens when you take a set of one vector, a set of two vectors, and a set of three vectors, and this set is linearly dependent. How do we interpret this linear dependence in our more like a down-to-earth terms, like a being zero, being parallel, being coplanar. We use this kind of technique with the solution when you just solve for one of the vectors, given that you know the coefficient next to it is non-zero. We use this kind of trick there too. This is like a broader scope of the same trick. Effectively, I'm telling you, I spent lots of time, I spent some time with the linear dependence. Effectively, this is one of the, in 9 out of 10 cases, there's a trick which you need to do the equation which involves linear dependence, this ability to solve for one of the vectors. But of course, you have to show your ability to, your capability of putting this in the right frame and supplying it with the right explanations, wording explanations. But apart from that, basically the sense of the whole linear dependence thing is this ability to solve for one of the vectors in terms of the other.